This is Dr. Manjunath from Government Women's College, Kolar. Title of my lecture is the basics of the elementary particles. Elementary particles are subatomic particles. Basically, they do not have the substructure. It is not composed by the other particles. For example, neutron is an elementary particle, proton is an elementary particle. For example, you can take the nucleus. Nucleus is composed of what the protons and the neutrons. That is why nucleus is not called as the elementary particle, whereas neutrons and protons are called as the elementary particles. Nucleus is having its own internal structure. Based on the types of the interaction of the nature, the elementary particles are classified into four types: gravitons, photons, leptons and hadrons. So there are four types of the interactions are possible in the nature. Those are gravitational interaction, electromagnetic interaction, weak interaction and strong interaction. Gravitons are the interacting particles in the gravitational interaction. Photons are the interacting particles in the electromagnetic interaction. Leptons are the interacting particles in the weak interaction, and hadrons are the interacting particles in the strong interaction. So leptons are usually having the masses between the masses less than the mass of the pions and having the angular momentum of half h cross. Hadrons are, as I explained, participated in the strong interaction. That means hadrons are usually participated in the between the nucleon interactions. This slide shows the classification of the elementary particles. Elementary particles are based on the classified into two categories based on the spin. First is what the bosons and second is what the fermions. Bosons are elementary particles having the zero or integral spin. Fermions are the elementary particles having the half integral spin. Bosons are further classified into massless bosons and mesons. Massless bosons are photons and the gravitons. These massless bosons are having the zero charge and the zero rest mass. Mesons are the elementary particles having the masses in between the mass of electron and the proton. Mesons are further classified into three groups: eta particles and the pi mesons and the k mesons. And this eta particles, pi mesons and k particles are based on what its masses only. So these pi mesons are having the masses in between the 260 to 280 times of the mass of electron. This pi plus meson is having the 273.9 times of mass of electron. Pi naught meson is having the mass of 264 times of mass of electron. Again, these k mesons are classified into the four groups: k plus mesons, k minus mesons, k naught and antiparticle of k naught mesons. Again, this classification is based on the charge and the mass. Another type of the another part of the elementary particle is what the fermions. Fermions are classified into the two types of the particles: leptons and the baryons. Leptons are elementary particles whose masses are less than the pions. Baryons are elementary particles whose masses are greater than or equal to the mass of the proton. So the leptons further grouped into the three categories: electrons and the muons and the nuons. Electrons having the mass of 1 times of mass of electron. Again, this is what muons are having the mass of 206.8 times of mass of electron, and nuons are having the masses of 0, that is 0 rest mass. Nuons and new muons are having the 0 rest mass. And coming to the one more category of the fermion, that is a baryon. As I explained, the baryons are having the masses greater than the mass of the proton, greater than or equal to the mass of the proton. A baryon whose mass is equal to the mass of the proton, then that baryons are called as the nucleons. Neutrons and protons called as what? The nucleons. neutrons having its own antiparticle called the antineutron, and proton are having its own antiparticle called antiproton. The baryon having the masses greater than the mass of the proton, so that baryons are called as hyperons. Hyperons are grouped into the four categories: lambda particles, sigma particles, xi particles, and omega particles. And lambda particle is having the highest mass, that is 234 times of the mass of the electron. So this is what the classification of the elementary particles. This slide shows the fundamental properties of the elementary particles. The first column of this table shows what the particle names, and second column shows the symbol of the elementary particle, and third column shows the mass or rest mass of the elementary particle in terms of the mass of the electron, and the fourth column shows the mass charge of the elementary particle in terms of the charge of the electron, and the fifth column shows the spin of the elementary particle, and last column shows what the corresponding antiparticles. The fundamental interactions in the nature are classified into four groups. There are four types of the fundamental interactions are possible in the nature. First is the gravitational interaction, second one is the electromagnetic interaction, third one is weak interaction, and fourth one is the strong interaction. Gravitational interaction is the interaction between the two masses. It is weakest interaction in the nature. It is always the attractive nature and has a infinite range, obeys the inverse square law. F is inversely proportional to the square of the distance between two masses, like that. And second type of the interaction is what the electromagnetic interaction. It arises between the interaction between the charges. It is the charge dependent one. Between the like charges, it is always repulsive. Between the unlike charges, it is always attractive nature. It also obeys what the inverse square law as explained by the Coulomb's law of electrostatics. And third type of the interaction is the weak interaction. So this is the interaction during the decay of the unstable nucleus. For example, alpha decay, beta decay, etc. So it is what the shortest range. And last type of the interaction is what strong interaction. It arises between the nucleus, between the neutron and neutron, between the proton and proton, and between the proton and the neutron. It is the strongest interaction in nature. It is always having what the attractive and it is short range interaction. To summarize the four types of the fundamental reaction, I have given the table here. The first column of this table gives the type of the interaction, and the second column gives the relative magnitude strength. So gravitational interaction is having the magnitude strength around 10 to the power of minus 39, whereas electromagnetic interaction is having the strength in terms of what, minus 3, strong interaction 1, and weak interaction is minus 14. From this column, so it is clearly observed that the strong interaction, that is between the nucleus, is the strongest interaction, and gravitational interaction is weakest interaction in nature. And third column gives what the range of the interaction, both for gravitational and electromagnetic interaction having the infinite range, whereas the strong and weak interaction having the range greater than the less than the 10 to the power of minus 15 meter. Carrier particles for this interaction is given in the fourth column. Gravitons are the carrier particles in the gravitational interaction. Photons are carrier particles in the electromagnetic interaction. Pions and kaons are the carrier particles in the strong interaction. So bosons are what the carrier particles in the weak interaction. And the fifth column gives what the particles affected. Hadrons are affected by the gravitational field. And again this charged particles affected by the electromagnetic interaction. Hadrons and leptons are affected by the strong interaction. Almost all elementary particles are affected by the weak interaction. And last column of this table gives what the interacting time. So 10 to the power of minus 16 seconds for the gravitational interaction, minus 20 seconds for electromagnetic interaction, minus 23 seconds for strong interaction, and minus 10 for this weak interaction. All the elementary particles obeys the 6 conservation rules, that is the mass energy conservation, linear momentum conservation, angular momentum conservation, and the electric charge conservation, lepton number conservation, baryon number conservation. This lepton number is what? Just a number assigned to the leptons. If the lepton is having the positive charge, simply it is assigned as +1. It is having the negative charge, then it is assigned, lepton number is assigned to the -1. If it is a 0 charge, then the lepton number is 0. Similarly, for a baryons, a number is assigned. That is what the baryon number. If it is a positive charge, baryon number is +1. If it is a negative charge, baryon number is -1. If it is a 0 charge, then baryon number is 0. That baryon number and lepton number is also considered in what? Almost all elementary particles. In addition to that 6 conservation laws, the strong and electromagnetic interaction obeys the additional 3 conservation laws, that is conservation of isospin, conservation of hypercharge, and conservation of the strangeness. So, for example, collision between the proton and proton. In the collision between the proton and proton, so lambda particle is emitted, and again the k dot particle and proton and pi plus particles are released. If we analyze the conservation of isospin in this particular nuclear reaction, in the LHS, the isospin the quantum number is +1, whereas for here, for proton +1, in LHS +1. So again in the RHS also, again this is what the +1 and -1, that is what LHS is +1 and RHS is +1, so that the isospin is conserved here. Whereas in case of the conservation of hypercharge, so here the proton is having the hypercharge of +1 and pi is having the +1. So LHS is +2, RHS is +2, hypercharge is conserved. Strangeness is also conserved in this particular reaction. For example, for the proton, strangeness is 0, whereas for the lambda particle it is -1. For pi plus, it is the -1. RHS, the LHS, the strangeness is 0, and RHS also strangeness is -1 + 1 0. That is why the strangeness is also considered in this reaction. I mean to say that in addition to that 6 conservation laws, this electromagnetic and the strong interaction obeys the isospin conservation, isospin hypercharge conservation, and the strangeness conservation. The last topic of this elementary particle is what? This quark model. This quark model is what proposed by the Murray Gell-Mann, American physicist. So according to him, 12 fundamental particles are building blocks of the universe. Among the 12, 6 quarks comes and 6 leptons comes. That means 6 quarks and 6 leptons are building blocks of the universe. A quark is defined as a point particle, no internal structure. It is having the fractional charges. The quarks are combined to form the hadrons. Most stable hadrons are the protons and the neutrons. Again, these protons and the neutrons are composed of the 3 quarks. So there are 6 types of the quarks are there. That is what? The up quark, down quark, charm quark, strange quark, top quark, and the bottom quark. And each baryon is made up of the 3 quarks, and each antibaryon is made up of 3 quarks. Similarly, each meson is made up of the 1 quark and 1 antiquark. It is diagrammically represented here. So this is what the meson, it is composed of 1 quark and 1 antiquark. And the second picture shows the quark combination of baryon. It is composed of the 3 quarks. If it is antibaryon, it is composed of 3 antiquarks, like that. So this slide shows the quantum properties of the quarks. So the second one, the first column is what? The quarks and antiquarks. Second column is what? The symbol for the quark. And third column is the electric charge. And the fourth column is what? The baryon number. Fifth column gives the strangeness. And sixth column is the charmness. And the seventh column is what? The spin. All these things are just a quantum numbers. Charm, strangeness, spin, baryon number, all these things are just a number assigned to the quarks, and there is no physical significance for these quantum numbers. And the second horizontal line, sigma minus, sigma naught, lambda, sigma plus belongs to strangeness minus 1. And the third horizontal line, this cascade minus cascade 0 particle belongs to the strangeness minus 2. And similarly, these diagonal lines are corresponds to what the charge q is equal to minus 1 for the sigma minus and again cascade minus particle, and for the cascade 0 and the sigma, lambda and neutron having the charge 0, and the third diagonal line of the second figure corresponds charge is equal to 1, q is equal to 1 for sigma plus and the proton. And the third diagram of this slide shows what the baryon decouplet. Here again these baryons are arranged in the systematic manner. So the first horizontal line corresponds to strangeness 0, that is delta minus delta 0, delta plus plus, and second horizontal line corresponds to the strangeness minus 1. Third horizontal line of the third figure shows the strangeness minus 2, and last horizontal line of third figure shows the strangeness minus. That means this omega minus particle is having the strangeness of minus 3. And similarly for horizontal lines, the first diagonal line having the charge minus 1, and second diagonal line of the third figure shows the charge 0, and third diagonal line of this third figure shows what the charge 1, and last diagonal line of the third figure shows the charge plus 2. If we remember these three diagrams, then we can able to remember the quantum properties, almost all quantum properties of the elementary particles. How to write the quark combination? To write the quark combination, we must remember this table which represents the charge and the strangeness. Charge for u quark is plus 2 by 3, d quark is minus 1 by 3, s quark is minus 1 by 3, and strangeness for u and d quark is 0, whereas strangeness for the s quark is minus 1. And one more important point to write the quark combination is identification of the particle. If it is identified as a baryon, then 3 quarks must be used. If it is identified as a meson, then 1 quark and 1 anti-quark must be used. I have given few examples here. For proton, it is identified as a baryon. It is having charge of plus 1 and strangeness 0. We must select a 3 quarks such a way that its net charge is equal to plus 1 and strangeness is equal to 0. So if we select the quark UUD combination, so u quark is having 2 by 3 plus 2 by 3, and d quark is having minus 1 by 3, minus 1 by 3. The net charge is plus 1 and strangeness is 0 plus 0 plus 0, that is what the 0. The quark combination UUD satisfied the properties of the proton. That is why we can call the UUD is the quark combination for the proton. Similarly, the neutron is identified as a baryon. Its proper net charge is 0 and strangeness is 0. So the quark combination UDD. So u quark is 2 by 3, minus 1 by 3, and again this is what minus 1 by 3. So quark combination becomes what the net charge of this quark combination is 0, strangeness is 0. That is why this is recognized as what the UDD is recognized as the quark combination for the neutron. Pi plus meson, it is a meson, charge plus 1, S0. If you write 1 quark and 1 anti-quark must be used. The quark Q is having charge of 1 by 3, D bar is having the charge of plus 1, so net charge becomes plus 1, strangeness 0. That is why UD bar is what the quark combination for pi minus meson. Similarly, for K plus meson, US bar, and for omega minus, it is the different particle of charge minus 1 and strangeness plus 3, and it is recognized as baryon. We can use 3 quarks. If you use the 3 S quarks, its charge becomes minus 3, minus 1 by 3, minus 1 by 3, minus 1 by 3, minus 3, and strange becomes what? The minus 3. That is why, so it is triple S is recognized as quark combination for this omega minus particle. So I have given only a few examples. You can try to write the quark combination for the other. Finally, the important questions of this chapter is classification of elementary particles, difference between the fundamental interactions, and the conservation of elementary particles, and again a brief note on the quark model and how to write the quark combination, that is the writing of quark combination for the elementary particles. Thank you for your patience.